you very much, and thanks for having me. I'll make this even worse, because most of this was actually developed while I was in Edinburgh a few years back, so it's kind of a bi-institutional effort. But yeah, just as a brief intro, I'm someone who works at the interface between direct numerical simulations and asymptotic methods for interfacial flows. And I tend to come in two flavors. So the sort of high-octane MATLAB side of me likes to work on violent things. Violent impact, splashing problems, jet breakup, these types of things. Whereas the other side of me is much more mellow and likes to work on slow systems where you really have to prod them either mechanically or electrically to do stuff. So I think today you're getting the first part of this. I'm going to talk especially about drop impact with an aeronautical flavor. So it's motivated by a brand with industry. And I'll just jump into it. So the story with this one goes that I was finishing up my PhD on small-scale electrohydrodynamics a few years back, and my supervisor at the time just walks in and says, "Radu, I have brilliant news. We secured a new grant. It's on drop impact and it's very exciting." I'm like, great. And the meeting is next week. And we started the project 6 months ago. So it was a very steep learning curve for me in this one, but it was definitely one of the most enjoyable ones I had, so I'll welcome the procedure. So I'll tell you what the context is. We're looking at aircraft interacting with what they call high liquid water content regions, which is code for clouds. We have plenty of them above Heathrow, so no shortage. And there's really two regions that we're worried about. So of course it's kind of the leading side of the airplane that's the problem. We have either wings, the nose of the aircraft, or what's called the nacelle, the bit that houses the engine. This is actually the most dangerous bit, because if you have water forming here, and it's subjected to low temperature, it accumulates, it freezes, then bits of the ice going into the engine spell a lot of danger. So the whole grant was structured around redesigning the nacelle and the icing prevention techniques and things like that. So I tried to translate this into a way I could understand it as an applied mathematician. So the simple problem in my book is, if I have a solid surface, and I have a droplet impacting it, and the droplet is characterized by a certain size, velocity, and impact angle, how much of it sticks, and how much of it blows off. The part that sticks is the dangerous one, because it may accumulate and turn into ice. The part that blows off is pretty harmless, but we need to quantify this. And you'll notice that I put a few key governmental agencies there, so this came at the same time when the regulations got hyped, because this is actually, after human error, the second most likely cause of aircraft incidents. So they were quite serious in making sure it's safe from this perspective. So you'll be fair to ask at this point, since planes are up in the air and certified, how do they do it at this stage? And the technique is pretty much as follows. So you have to imagine you have an aircraft which is meters long, and the droplets tend to be tens of microns to hundreds of microns large. So your only choice, because it's such a difference in scales, is if you want to consider it everything at once, you stick in the wing or the nacelle or whatever you have, you compute the airflow around it using your favorite CFD solver, and on top of that, you then put droplets, which actually are modeled as particles. So you take two of them, a certain distance apart, and you follow them and see exactly where they land on the surface. And you take the ratio between their starting distance and their final distance, call this a beta curve, and multiply it by the liquid water content of the cloud, which is really a density, and this is what's called the retention profile of the aircraft. When I read about this, I was scared, I'll be honest with you, because it ignores all the fluid dynamics. You effectively consider the particles as being solid, non-deformable, there's no two-way communication, you just put them on top of the airflow, and you compute them as OD trajectories. So basically you're killing off all the interesting parts of the flow, and you're just taking big enough safety margins to ensure that you're safe. So it wasn't a great start from this perspective. From the other side though, kind of the traditional drop impact area is a very rich one. So the first experiments on splashes of individual droplets date back almost 150 years ago by this gentleman named Worthington, and he actually did a really cool experiment. So you have to imagine that this was in the early days of photography. And in order to study and sketch the ones you see in the middle row there, what he did is he took droplets and released them from a certain height, but at the same time he had a marble, so that they were released in tandem and in a dark room. And as the marble hit the surface, it generated a spark, and the spark was enough to expose the whole thing so that he could draw the actual sketches on it. So, and these are the current day equivalents of those. And you'll see there's still quite a few differences in terms of fingering patterns and so on. Many of them are attributed to all sorts of surfactants lying in the film photography equipment. So there's still ongoing questions even about this simple one. But what I'd like to point out is that this is a very nice setup to study because it's a very rich problem. You can actually do experiments yourself. So it's very fun to do in schools. What I typically do is, my favorite liquid is beetroot juice. And I take one of these pipettes and a piece of suitable paper, and you can drip them from different heights, and you'll see very different behavior, so I sketched a few there. If you drop it from a low height, you'll just see something like a spherical cap, and there's a certain contact angle. If you put it a bit higher up, you'll see it spread a bit more, and it becomes thinner, of course. And if you go even higher, you're still seeing all sorts of interesting instabilities and eventual splashing and so on. But the fact that it can be seen with the naked eye is very helpful in this scenario. So of course, I'm speaking from the aero perspective, but this is of relevance to inkjet printing, combustion, pesticide spray, all sorts of other things. And people are interested in a few simple questions about these, at least to begin with. So when you have a drop of a certain size impacting with a certain speed, even at 90 degrees, what is its maximum spreading diameter? What is the height of the liquid film at the center? They're all fairly easy to phrase questions that we can find answers to. So just out of curiosity for, let's see, front row, now you're regretting where you're sitting. If I were to ask you what parameters are important, what would you say? Things like that. Yeah. Reynolds numbers, Weber numbers, Ohnesorter numbers are pretty much the ones. People have been thinking about various ways to phrase these in terms of the drop quantities for the better part of a century or so. And a very interesting experiment came by in the early 2000s by Sid Nichols' group in Chicago. I'll just show you two quick movies. So this is an ethanol drop that's a couple of millimeters in diameter, and it's hitting the surface and is producing what's called a corona splash. So this beautiful crown that forms. Now you take the same droplet with the same velocity, and you only change one thing. But the behavior is going to be drastically different. So can you guess what happened? It's subtly hinted in the slides, but the only thing they modified is the pressure in the lab. So effectively, the properties of the ambient gas. So it had nothing to do with Reynolds numbers and Weber numbers, it had nothing to do with quantities in the drop, but it means that all, or at least a good part of the efforts of classifying splashing dynamics in the past have missed out on quite a critical piece of information. And if you want to put it in more romantic terms, a drop that splashes in your lab may not splash on top of your mountain and won't splash on the moon, so it really matters where you do these experiments. But from our perspective, it's really cool because on the one hand, we now have the experimental gear to look at very small scale features that haven't been there 10 years ago. We now also have the type of codes, algorithms, and computing structures to study these alongside them, and this in turn informs all the analytical effort we can make. So it's kind of the ideal trifecta for this type of problem. So I'll jump into the numerical part, which is the one I like best for this particular project, and we touched upon this yesterday as well. We have a problem, it involves interfaces. What do we use to solve it? So this is a recent review on possible methods for interfacial flows, and you'll see everything from LBM to interface tracking, interface capturing. These are the diffuse interface methods. There's like 50 methods at least in subcategories. So how do you know which one to pick? Well, it really depends on your problem. So there's not one of them that will solve every single problem. You have to miss out. For my particular case here, I'll now have very large differences in densities and viscosities. And because I'm studying splashing, I know I have topological changes. So drops forming, drops breaking up or coalescing and so on. So for me, using something like an interface capturing method and in particular a VOF or a hybrid level set VOF technique is the way to go. But for example, in a problem where you don't have breakup and you care more about physics on the interface, you may be better suited by a front tracking method or by a diffuse interface type of method. What I'm telling you here, though, is don't blindly trust a certain method to solve all of your problems. Make sure you know what you're sacrificing and why you're doing it before you start. So now I'm going to use something called JERS for simulations. The name comes from the insect that walks on water based on surface tension. It's called Jerris lacustris, the water strider, and it has a younger brother called Basilisk, which walks on water based on inertial effects. It's a finite volume code. It's adaptive, second order in time and space, and it's written in C. It's open source and pretty nice to code up in. And in terms of what's under the hood, you're doing the one fluid formulation, so you're solving the Navier-Stokes equations in the entire domain. You have this type of color function, which is used to migrate from fluid 1 to fluid 2 in this format, and then you advect it with the velocity field. So it's nothing unusual in that sense. but it's very helpful and useful for these types of problems that involve topological changes in general. And you'll be happy to know, A, David, that it does automated testing and all the nice things we talked about in the past, and Prash, that it doesn't do the steady state turbulent tutorial. So I think it covers the key people in the crowd. Good. So I alluded to the difference in length scales and that you can have a plane and droplets at the same time. So I'm going to make my first approximation, and that is to say if my droplets exist at a kind of a domain of size of millimeters, but my body is of size meters long, effectively the drop won't really care about much of the domain. And actually what I'm going to say is that when every drop comes in towards the surface, what it sees approximately will be a straight surface. It may see it at being at a certain angle, so I'll have to keep this in the parameter, but the actual curvature of the surface will not be important just because of the difference in the radii of curvature between the two bodies in question. And in this case, I can study it from the perspective of an oblique stagnation point flow. So this is a flow where I have a solid boundary, and from the opposite one, I impose a flow coming in, a uniform flow coming in at a certain angle. It will have one stagnation point, and it will have boundary layers forming on either side of it. This is nice for this problem because if I then put the droplet here, it will have a uniform flow and it won't get shattered when it starts. And as it nears the body, it will see the same type of boundary layers it will see on the aircraft surface with, of course, the due approximations I've made. So we wait until this one reaches steady state. We put in the drop in the DNS. It's fully coupled. You have all the fluid dynamics in, and we see what happens. So I'll do a bit of foreshadowing. If it's a small drop, it's spherical at the beginning. It will remain spherical quite close to the surface. It hits the surface, pancakes, and then retracts under surface tension and remains as a spherical cap. So that's relatively boring. If it's a moderate sized drop, if you follow it carefully, you'll see that it deforms quite a bit. It becomes ellipsoidal, it starts to bend, it hits, it forms all sorts of droplets. There's quite some action there. And if it's an even bigger droplet, you get what I call violence splashing. I mean, you already disintegrate the drop before impact, and when it hits, it shatters into tens of thousands of droplets. And when you see something like this, if you're as skeptical as I am, you should ask yourself, well, that looks like a bloody mess. How do I know it's right? How can I validate? What can I do to actually understand what's going on in this flow? So I like to split the story into three parts: pre-impact, impact, post-impact. For pre-impact, we're going to rely on experiments. There's one group affiliated to the Spanish Ministry of Defense that they have a room, they have a rotating arm with an airfoil at the end of it, and they have a drop generator that releases droplets that fall slowly in relative terms under gravity, and they image how they deform as it gets close to the surface. I'll show you a video. So we visited them a few months ago. This is the rig operating at 10% of the speed. It can go up to 100 meters per second in angular velocity. I like to use the visual bucket norm just to show you how the room works. So somewhere here in a few seconds, you'll see that. Yep, for sure. So the room is shaking considerably. It's triple reinforced glass. At some point they lost a screw in an experiment and went through all the walls a few years ago. So then they doubled the wall size yet again. But yeah. They have this nice setup here, and what they get out of it is pictures like these. So these are small drops, moderate-sized drops, large drops. For small drops, you can barely get the resolution in, but like you can see, it's a pretty ellipsoidal shape. As you make them bigger, they start flattening and becoming more and more ellipsoidal, and eventually you undergo this sort of top hat type of deformation, and you break up into a cloud of droplets. So we can mimic their setup in this sense, minus the gravity, which is not important, and compare like for like. It's not a perfect comparison, but we can get the kind of aspect ratio change in the droplet in very good agreement with what they do, and we can classify the various regimes. The interesting bit is that while they cannot get too close from certain perspectives, we can, and vice versa, so we can complement one another, and then we have a kind of combined setup in place now to do a more rigorous set of experiments. But this is the first comparison we can make in pre-impact. On impact, we're going to use analysis. So on impact, there's this beautiful theory called Wagner theory. Who's heard of Wagner theory? Yes! It's very rare. Usually, when I do this presentation in the US, everybody stares at me for 5 minutes. It's great. So Wagner was a German gentleman in the 1930s. I invented this theory for ships landing, planes landing on water, basically to find body forces on the bodies hitting water. And you can use it for liquid-liquid impacts, liquid-solid, solid-liquid. You just change a boundary condition. I'm going to do the liquid-liquid one because this is just convenient for this particular setup. But I've listed my sins here. So I'm throwing away everything except inertia. It's a high-speed problem, and I'm going to assume that everything except inertia is going to die out. I have two important parameters: the relative ratios of these, relative radii size between these two droplets, and their relative velocities. And with this, I'm going to try to use something to kind of calculate how the jet in between them operates. So I'll skip these. This is what it rests on. What we want to study is this region in particular where the jet is born and starts extending. And in terms of how the asymptotic structure is laid out, you have an outer region that keeps the shape of the drop, you have the inner region that's the actual root of the jet, and you have a long, thin region that extends along the jet with typical techniques for each. So I'll show you a taster. Because it's a nice inviscid flow, then you can introduce velocity potentials, you reduce them to Laplace equations, the favorite tool of any applied complex analyst. And what you really solve for here, because it's pretty standard in terms of conditions, is actually this moving point. This is the root of the jet, but from the outer region perspective, you see it as a point that's just moving. And then to match, you need to zoom in, and when you zoom in, you have this type of structure. It's a free streamline flow, a Helmholtz type flow, and you can solve it using Schwarz-Christoffel mappings. I won't bore you with the conditions, but I'm happy to talk about them if you're interested. But what you get out of this is a jet thickness and a jet velocity. And then when you go into the jet region, you move in a suitable coordinate frame that bends with the jet. But then you can formulate those types of shallow water equations in it, solve them with characteristics, and you get everything analytically. One thing I'll mention is that you can get very easily measurable things out of this. The position of the root of the jet, the velocity, the thickness. I'll show you one simulation that matches it. So when it's a symmetric situation, and I'll stop here, what the analytical framework does is it describes this part relatively well. What it won't do is tell you anything about the tip of the jet, the entrapped gas in between them, and things like that. So you know what you're missing out on and you can correct for it, but that's about it. And before I show you the comparison, I'll just mention that these are not simple computations. So 1,000,000 degrees of freedom, a few days on large CPUs, they take up a lot of time to automate, to post-process, pre-process. On the other hand, with the analysis, you can do it carefully, it takes a couple of months, but once you're done, you're done. The only downside is, this is my collaborator before and after he started. You know, yeah, but it's been good fun. So in terms of the comparison, I'll be quick about it, but the symbols represent the numerics, the curves represent the analysis, and while you're at early times where the conditions of the asymptotics hold, everything is great. So I'll just close with one point, which is to say, how do we use this at the end of the day? We came to the engineers with our conclusion, we understand things that happens at the level of an impact. I haven't showed you a part of it, but the point is we can now create virtual clouds with more of these droplets, and using the self-similarity in the domain, we can actually populate them with a virtual cloud of droplets. And it turns out that there's an interesting analogy between the beta curve and the type of input parameters like the angles, velocities, and so on we can give our system. So what we propose is this type of multi-scale approach in which both my scales are continuous, but one of them includes the actual body and the other one includes the droplet. And what we do is we say, okay, we trust your particle up until the point where it gets close to the surface, but then we don't trust it anymore. We want to take all the parameters we can, populate our DNS space, resolve everything carefully there, and then jump back up and feed the quantities into the types of solvers you use later on in the process. So yeah, with that I'll just close by mentioning that there's a lot of interesting problems still at stake. I haven't mentioned anything about freezing temperature effects, compressibility, so there's lots to do for years to come. There's interesting computational science problems as well there, because these generate quite a lot of data and they need specialized algorithms to cope with it. But yeah, it's definitely an interesting thing to get into. And yeah, with that, I'll just close by mentioning that there's a few interesting articles I like to write about this if you're just curious about the layman applications. There's a YouTube channel that has a lot of splashes and things. And I'll thank my collaborators and the institutions that pay my carbon footprint. So thank you for listening.
Thank you. We have about 5 minutes for questions.
Radu, nice talk. So in terms of, especially when you have a Smash,
Yeah.
I think it may be worthwhile telling the audience on what are the contact line bar regulations you do at the point, because CFD software have nonsense in them.
Yeah.
And it's very important to know the physics of what is happening in the contact line to get the results what you have.
Mm-hmm.
So
Sure. Yeah, I'll comment a bit on that. So I'll quickly show you one of the simulations again, and if you'll follow the contact line, it'll justify a few of the things I'm saying. So once it hits, it will entrap a little bubble underneath, but it will spread, and then it will retract. Now, it turns out that actually for these highly inertial regimes, what you do during the spreading stage doesn't really matter. You can pick a static contact angle of any type, you can pick another more clever model, the spreading part won't be affected. What will be drastically affected is the retraction part. So exactly how you choose your advancing and receiving contact angles matters quite a bit. In this particular piece of code, what I've done is we have a dynamic adaptive contact angle model based on the Cox-Voigtman matched asymptotics rule, where you can set a few of the things. Numerically, what tends to happen is if you zoom in at the half-cell distance away, you measure the velocity above, and you advect it with that, and then you adjust the angle accordingly based on the asymptotics model that underlies it. So it's a fairly subtle technique, and it's quite easy to break it if you're not careful. But provided you, so VOF methods are notoriously bad in terms of resource usage because you have to throw in a lot of degrees of freedom where you need them. But if you're careful with it, you can do this and make sure that mass is conserved and everything is running nicely. You just have to do the validation test. Yeah, good point.
I noticed in the videos that you played, there's a general kind of fourfold.
Yeah.
Is that something you see or is it the mesh that?
That's, let's see, I'll blame my cluster people on this one. So what tends to happen here is I work on 3 types of clusters, 3 different sizes, and the ones we have locally that can produce videos don't have enough capacity for me to throw in all the degrees of freedom I need. So you actually see the artifacts of the fact that we're using a quad 3 or 3
But are you actually starting with normally axisymmetric conditions?
No, it's full 3D. It's basically, you're seeing the effects of a
So
curved
what's the
interface.
initial condition?
The initial condition is a uniform velocity in a 3D droplet on an otherwise cuboid type of domain.
But it's the initial condition is trying to be axisymmetric.
Yeah,
You're
exactly.
not seeding it with something.
Yeah, because in many of them I do oblique anyway, so I need the 3D.
Oh yeah, I
yeah.
appreciate it has to be 3D because you have
But-
really interesting stuff there.
so
but you did,
When you go up
you didn't
a
give
step
a
or two
representation.
in resolution, you get more out of it and you stop seeing those artifacts. It's just I can't make videos at that level of resolution. But yeah.
My question is about your initial video that you showed. That they were testing the same droplet, the same
Yeah.
surface, but you were seeing different behavior on this plasma. What was the pressure difference between those 2?
Factor of 5.
Factor of 5.
I think one was 100 kilopascals and one was 17 point something. Yeah.
Oh yeah.
Yeah, it's a fairly well documented, I think it's a PRL paper, and they have a few subsequent studies in JFM as well, if you want to have a look. Sid was kind enough to visit us a few years ago while I was in Imperial, and now they're more keen on doing impact on the oblique surfaces, which is quite relevant and a happy situation for us.
Can also be affected by the size as well, if you have the same conditions.
About the?
Yeah, the same situation, same conditions, same pressure difference, but
Yeah.
different size.
Oh no, it's a major player. I mean, the size of the drop, feeds in linearly to both Reynolds and Weber numbers, and even with a factor of 5, either way, you can get quite dramatic effects. Yeah. It's a problem that's very sensitive to the conditions, and it has 20 parameters I can come up with at least. So, there's no shortage of manpower needed.